Hello. In this video, we examine our second conic section. In fact, one of the most popular ones that you've probably seen before, the parabola. Let's get started. So remember that in our previous video, when we introduced conic sections, we described them as being formed by taking a double cone and slicing it with a plane at various angles. We looked at the circle last time, and today we're looking at this one in the middle, the parabola. Now, in your previous classes, parabolas were always functions, meaning they always opened up or down. That's about to change. We're going to look at parabolas left and right as well. Let's take a look at our next slide. So when we talk about a parabola, in this chapter on conic sections, we're not restricting ourselves to only functions. So we are allowed to see that parabolas could have one of four orientations. Opening up or down is definitely a possibility. And I wanted to point out to you that's what's happening in this case here on the left side of your picture there. Let me break that apart for you. So we see that on the left side of the picture here, we're opening up or down. Now in the equation, keep in mind what that will do is have something like y equals x squared. So we're used to that, right? Parabolas that open up or down have x getting squared, right? We're used to those. But when we're talking about parabolas that open to the left or to the right, like the ones on the right side of our picture, that's going to be the situation where instead of x getting squared, we'll have y getting squared. So that's a little bit different. And if you want to practice that, you could actually go ahead and practice plotting points. Let x be certain values, let y be certain values, and you'll start to realize and believe that when x is squared, not y, that's the parabola going up or down, and when y is squared, not x, that's the parabola going left and right. So feel free to practice with points until this becomes something you actually believe instead of just being told. A couple of other things I wanted to point out to you before we jump into those massive equations in front of you. I wanted to point out to you some new things that you haven't really talked about before. And those new terms are the word vertex, which you have heard of, and the new ones would be focus and directrix. So let's take a look at the parabolas in our picture. Notice here, for the parabola opening up, that lowest point was called our vertex. Usually we refer to that as V for vertex, right? So that vertex was our minimum, and in the case where it was opening down, the vertex was our maximum. Now, when the parabola opens left or right, that's also the most extreme point in the orbit. So that's going to be our vertex here, and this would be our vertex in that situation. But as far as the other two new types of information, the focus and the directrix, let's take a moment to define each of those. When we mention the focus, that's going to be a point inside of the orbit of the parabola. So for example, this point here, this is what we mean by our focus. This point below the parabola opening down is our focus. This point to the right of the parabola opening right is our focus. And this point to the left of the parabola opening left is also our focus. Now, that distance from the vertex to the focus is very important. We have a name for that as well. There are a lot of letters on this slide. And that name is the name P. So what is P? P will be our distance from your vertex to your focus. So if P is 2, that's how many units away your focus is from your vertex. So that's our distance P that we're talking about here, the distance from the vertex to the focus. Now, why is that so important? It turns out P is also the distance from the vertex to a line which is going in the opposite direction from the vertex that the focus was. So let me use another color for that line. How about, let's pick one here. I haven't used black, what might work. So this line here, you can see that okay? Yeah. This line here, which goes in the other direction than the focus went from the vertex, is called your directrix. And I'll use D for directrix. That's what that line is. When it's opening down, the vertex, sorry, not the vertex, the directrix will be above that parabola. When the parabola is opening right, the vertex will be behind it to its left. There will be its directrix. When the parabola is opening left, that line, that directrix, will be to its right. So it always goes in the opposite direction as the focus and the parabola opening. Now, that P is really important because that P was not only your distance from your vertex to your focus, but it's also the distance from your vertex to your directrix. So that distance, again, P, is the same in this direction as well. So if it was 2 units in one direction to your focus, it's 2 units in the other direction to your directrix. Why do we care about these things, you might be wondering? Like I thought the parabola just opened up and that's all I cared about. Well, have you ever noticed that some parabolas are very narrow and some parabolas are very wide? Yeah, and they probably told you in your previous classes that had something to do with the coefficient of the item being squared. In other words, whether it was stretched or shrunk. Remember that? Well, it turns out we have a special approximation for that ability to stretch or shrink, and that is known as the coefficient of the non-squared term. So if you take a look in your formula here, down below, there's a lot of different things happening. But in these formulas, the coefficient of your non-squared term is known as 4p. And 4p has another name to remember. 4p is called the lattice rectum. Okay? The lattice rectum is going to be a line segment that cuts through the focus and is parallel to the directrix. I know we're throwing a lot at you on this slide, but hopefully in a few moments this will make some sense. What we mean by the lattice rectum in this situation would be if I were to take a line segment and draw it through the focus, and notice how it's parallel to the directrix below, that entire segment has a length of 4p. So if p is 2 units, that segment would have a length of 8. What if p was only 1 unit? Then that length would be 4. If p was 8, that length is 16, and now you've drastically widened your parabola. So the smaller the p, the more narrow the parabola. The larger the p, the wider that parabola, because the longer its lattice rectum. Okay, so with that information, we'll actually have enough information to know where the vertex is, how it's opening, and how wide to make it going through the focus. All right, with that information, let's take a look at the equations together. Remember that when x is being squared, it opens up or down. When y is being squared, it opens left or right. To know if it's up versus down or left versus right, that's where we look at the signs of our coefficient there. If they're negative, then in the vertical case, it'll go down, and in the horizontal case, it'll go to the left. So let's see if we can make our own equation for the example below. It says if you have a parabola whose focus is 2 units to the right, that's good information to know, of its vertex, and the vertex is at the origin, what equation would we have? I always recommend a quick sketch, so let's take a peek here. If our vertex was at the origin, I'll use red to be consistent there. If that was our vertex, then don't we know what HK is? Yeah, HK would be at 0, 0, okay? What else do we know if that's our vertex? Well, we know how it's opening, right? They told us that our parabola should be opening in which direction? Yep, to the right, because the focus is always in the same direction as your parabola is opening. So if I go to the right 2 units, that's where my focus is, at the location of 2, 0, it looks like, 2 units to the right of my vertex, which was at the origin. And now I know what's going on, don't I? Maybe you don't feel too comfortable yet, but you should know that it's opening to the right, towards the focus, okay? And if it's going to the right, in your equation, which variable should get squared, the x or the y? Remember which one's which? That's right, it should get y being squared. So we would have y minus k getting squared. If it's going to be opening right, should I make 4p positive or negative? That's right, positive 4p times x minus h. So this would be the original model before fitting in the information I have. Now let's fit in our information. Since we know that the vertex was 0, 0, couldn't I make this just y minus 0 or just y squared? Good. I'll leave the 4p alone for a moment. We'll come back to that part. But if x minus 0 is our next part, couldn't I just say x? It's a little less tacky. And now I just need to talk about p. If you understand what p is, you're in great shape here. P was the, go back to your notes here, distance from the vertex to your focus. So do we have p? Yes, we do. We were given p. P is 2. And you can see that in your picture that you've drawn. It's 2 units away from the vertex. If p is 2, then 4 times 2 is 8. And now we have the model that is actually representing our situation. So if this was an actual parabola in a real-life situation, a parabolic trajectory of some type, if you need to find an x value when you have a y value, or vice versa, you can simply plug them in, and you have your answer. And we'll be doing a word problem later at the end of the video, so you can see this in action. Okay, so once again, before you go on to any of the other examples in this video or attempt to try the homework, it is essential that you understand when you have a parabola, right, when only one of them is squared, x or y, recognizing which of the 4 orientations you have, and then learning what P is, the distance from the vertex to the focus in the direction that you're opening, and the distance from the vertex to the directrix in the opposite direction. Now, I still haven't really explained to you why you need those things. And so if you're wondering, why did you just teach me about all of these F's and D's, that's a great question. Let me go back to the very first blurb at the beginning of this slide. It said, what is a parabola? The parabola was the set of all points which are the same distance from a fixed point called the focus as they are to a fixed line called the directrix. Now we can hopefully understand what's going on. Let me pick a point on the first parabola in our picture here. Here's a point in purple there. It turns out that if this point is truly on the parabola, if I were to measure its distance to its focus, which was right there, and measure that number out, let's say that number was 4 units. And then if I were to take a line segment from that point down to the directrix, it better also be 4 units. They have to be the same. And it doesn't matter which point I pick on the trajectory of the parabola, the distance from that point to its focus and from that point to its directrix better be identical. If it's not, then we don't truly have a parabola. So that's what we mean by a parabola, and that's why we have to have the focus and the directrix. Okay, let's go practice what we've just talked about and see if any of this makes sense. In example 1, we give you an equation and say, analyze and sketch the graph of the parabola below. So first of all, how would you know that this is a parabola if I hadn't told you? That's right, only one variable is being squared. That means it can't be a circle like we talked about in our previous video where they were both being squared. Secondly, how do you know which of the 4 orientations we have? Well, if y is squared, how are we opening, left or right? Is it opening left, right, or up, down? That's right, it's going to be left or right because it's y and not x being squared. Now, how do we know if it's left versus right? That's right, it's a negative coefficient, so it must be left. So now we know how it's opening. We have a parabola opening left. Do we know its vertex? Be really careful here with its vertex, so its most extreme point on the trajectory. Right, well, careful, the h value is actually 3, isn't it? And the k value is -2, so your vertex would be at 3, -2. It's very tempting to just read from left to right, but you have to keep in mind that your h is always tied to your x and your k is always tied to your y. So watch out for those. So I'm going to go to my graph and plot that point. 3 to the right, 1, 2, 3, and 2 down, 1, 2. So this is the location of my vertex at 3, -2. Now, do we know anything else about this parabola? Yeah, we know its coefficient of x minus 3 is 8. So we must know what 4p is, don't we? So remember that in the standard form of a parabola, the coefficient of the non-squared term is known as 4p. That is the length of our lattice rectum, the line segment running through the focus and parallel to the directrix. So if 4p equals 8, do we have p by chance? We do. P is 2. Sorry, I keep using 2, but it's a nice, easy number. So if p is 2, that is the what? The distance from the vertex to the focus. So where is my focus? Well, the focus has to open in the same direction as your parabola, which was going to the left. So if I say I'm starting at my vertex and I'm going to the left, that would mean that my x value is changing, isn't it? So if you started at 3 and you go 2 units to the left, wouldn't your focus be at this location? So what is that point? Well, you could just subtract from the value 3. 3 minus 2 is 1. So when x is 1 and my y value is the same as it was for my vertex, -2, that's the location of my focus. So now I know how I'm opening. I'm opening to the left. But to get a better sketch, we could get our directrix and then we could get our lattice rectum. So where is the directrix? Well, it's 2 units in the opposite direction. So from the vertex, 2 units this way, I'll have a line. So I could draw a dotted line. You could draw a solid line. I just prefer dotted to remind myself that it's not really on the graph of the parabola, but it's just the imaginary line that everything is hooked up to, if you will, that goes through. Okay, so let's take a look at what this means for us. If our directrix is then a vertical line, what would its equation be? That's right, x equals what number? 2 to the right of the vertex. That's going to be at x equals 5. So that's the equation of my directrix. And if this parabola is opening left, we're almost done. The parabola is going something like this, but how wide or how narrow should we make it? Well, that's where we need the length of the lattice rectum, which is always 4p. So what was p? It was 2. If p was 2, 4p is 8. So here's what we know, that if we want to draw a line segment that goes through the focus and is parallel to the directrix, its total length should be 8 units, meaning I would have to go 4 units above the focus, so 1, 2, 3, 4. That has an x value of 1 and a y value of 2. And I would have to go 4 units below the focus, 1, 2, 3, and 4, which has an x value again of 1 and a y value of, if we started at the focus, -2, and we went down 4 units, that's at -6. So why is this useful? Well, now I know how wide to make my parabola. Let me fix it now. We have more information to fix this guy. Let's get our colors back. We'll use red, why not? So we're going through the vertex, and we're also going through those 2 points that were the endpoints of your lattice rectum. So our parabola is looking something like this. If you wanted an even better sketch, you're always welcome to find your intercepts. By letting x equals 0, y equals 0, you could get these locations of your x and y intercepts on your own. So feel very comfortable doing that. You can practice that skill so that you can confirm that this makes sense. Your focus was to the left of your vertex, 2 units. And one more thing that you could really make sense with is by checking that the actual definition has been satisfied. By that I mean this distance from this point here, let's say, to this focus here should be the same as it is to this directrix here. If it's not, then we haven't quite graphed this correctly. Okay? So we've done one example now of where we've given you the equation of a parabola in standard form. But let's take a look at a harder challenge. What if we asked you to come up with the equation in standard form when we've described the situation to you? So here we describe a parabola whose focus, let me get a color you can see, here we go. A parabola whose focus is at 0, 4, and whose directrix is y equals -2. I always recommend to students draw a little sketch to see what's going on. So if you were to draw a little sketch, 0, 4, sorry, it's a little ugly, 0, 4 would be somewhere up here on the y-axis. So let me get another color so that's easier to see. There's my focus at 0, 4. So if my focus is at 0, 4, but my directrix is the line y equals -2, this is the part where you really have to make sure you're not too sleepy when you're doing your homework. When you see y equals a number, is that a horizontal or a vertical line? Got to know what that is. It is a horizontal line. Good job. So y equals -2 would be down here, and we'd have our directrix at y equals -2. So if you got that part wrong, you're going to have a hard time getting the problem right. So this is our directrix. Okay. So now that we have our directrix at y equals -2 and our focus above it at 0, 4, can you figure out with me where the vertex is and how it's opening? We need those 2 pieces of information in order to get our equation, don't we? So where is your vertex? And what direction am I opening in? Once I have that, I'm really close to getting my equation finished. Okay? So how do I know where the vertex is? Some people just want a mathematical formula here. Technically, you're just looking for the midpoint between your focus and your directrix. So if you want a formula, if you understand the midpoint, you're finding the midpoint between 0, 4 and the y value of -2. So between like 0, 4 and 0, -2. Find the midpoint by averaging those values together and you'll have your answer. Personally, I just like to count here. I notice how far apart they are. They're a total of 6 units apart, which means the halfway point must be 3 away from each of them. So 1, 2, 3. I think that's a lot easier. But if you want to use the midpoint formula, more power to you. What is your vertex then? It's at 0, 1. See if that makes sense. You go up 3 units, you get the focus. You go down 3 units, you get the directrix. Hey, I keep saying 3. Isn't that p? P is always your distance from the vertex to the focus and the vertex to the directrix. So we've now found P, and we know how it opens. How? Well, it always opens in the direction of the focus. So it must be opening up. And we could get a better sketch, of course, once we put our latus rectum going through the focus, right, of 4P. So of 12 units, okay? It'd be wider than what I've drawn here. But as far as the basic idea, we know it's opening up. Because, why? The focus was above the directrix, which meant the vertex was opening toward the focus going up. Now that you know it's opening up, do you remember which variable should get squared in your equation? That's right, x. So the equation should be x minus h squared equals positive or negative 4p. If it's opening up, that's right, positive 4p times y minus k. So what do we do now? Well, we fit our equation with our information that we have at our disposal. We know what p is. P is 3, so its latus rectum, or its coefficient, should be 4 times 3, which is 12, which means that if I really truly wanted to draw a line segment going through the focus, it should have a total length of 12, 6 in each direction. Okay, what else do I know? Well, I know that my vertex was 0, 1, so this should be y minus 1, and x minus 0 is just x, so I could just write x squared equals 12 parentheses y minus 1. This would be my answer in standard form. I will tell you that in some textbooks, they'll go ahead and distribute that 12 and give you 12y minus 12, and then you'd have to work backward to get it in standard form. So be aware of that. Sometimes it's almost in standard form, but not quite. All right, so we've done 2 examples now. In the next example, we're going to put all of this together and see if we can apply it to an application. So let's take a look. Ooh, here we go, a lot of words. Quick note, when I teach overseas, the difference I see between Americans and non-Americans, Americans look at a word problem and they give up too soon. So let's not be that person. Let's go ahead and overcome. So when we read our first sentence, deep breath, find out what they're trying to tell me, and keep persisting. We can do this, okay? A radio telescope has a parabolic dish with a width of 100 meters at the opening. Even if you don't know what it's saying yet, look for a keyword. Keyword I see is parabolic. So we're talking about something that resembles a parabola when we look at its cross-section. Now, it hasn't told me how to draw the parabola yet. So when you're doing a word problem, you can actually draw the parabola in any orientation that you want. Most humans will choose up or right. So I'll choose up for now, but you could have chosen right. So I'm going to draw a little parabola opening up to describe a parabolic trajectory in general. Notice I also chose to put my vertex at the origin. That's just to make my life easier. You could have picked a different vertex, but just to make my life easy, I stuck my vertex at 0, 0. Okay, so you don't have to choose that easy situation, but I recommend it strongly. Let's continue with what else it gives me. Notice it says that the parabolic dish has a width of 100 meters at its opening. Now, why would it say something like this? Well, remember that in real life, or in math I should say, parabolas continue going on and on and on forever, okay? But a real situation, like a parabolic dish or a satellite dish or something like this, would actually have an ending point. It might be shaped parabolically, but then it stops, doesn't it? And that's what's happening here. So let me show you what I mean. This dish might be going something like this and then stopping. Okay? And what they're telling us is that at its opening, it has a width of 100 meters. Can you now kind of think about where that 100 meters would be? Where would it be? That's right, it would be this entire distance across. So if that entire distance is 100 across, 100 meters, can you tell me anything about the location of those 2 endpoints? Supposing, of course, that we had centered this vertex at the origin. Well, yeah, you would know that this x value is at x equals 50. And this one here, let me get some more space so it's not so hard to read for you. This one would be at negative 50, wouldn't it? Now, that's really important information. We're told 2 points on our parabola. That might be helpful to us. Now, you might be thinking, what about the y-coordinate? You didn't give me that. Well, maybe I didn't, maybe I did. We've only read sentence 1. But as we read, we try to write down a description of what's happening. What is this reality that we're talking about? Okay, one thing to also note, when you're doing a word problem, it's really important that you don't read too much into the problem. In other words, don't assume things that aren't explicitly spelled out. What do I mean? Well, remember how we've been studying parabolas and latus rectums, and how latus rectums go through the focus? A lot of students, as soon as they draw a line segment like this at the opening, they think there's the latus rectum. But the only way that's guaranteed to be the latus rectum is if we know that at the opening, the focus is exactly at the opening, I should say. If we aren't told that the focus is at the opening, we can't assume that we have the latus rectum. In other words, we don't know that 4p is 100, is what I'm trying to say. So be really careful not to assume that. Now, we've only read sentence 1. Let's head over to sentence 2. In sentence 2, it says, the collected radio signals are reflected to a single collection point, and that collection point is called the focal point. Now, that's a pretty good indicator. If something is called a focal point, it kind of sounds like focus. You're focusing in on a point. And they're telling us that it's 45 meters from the vertex. Now, typically, if you have a dish of some type, think about like a satellite dish, and it's focusing in on a single point, typically that point is beyond its opening. So I would probably venture a guess that that focal point, called our focus, is somewhere beyond our opening, okay? So if that is the case, we now know that is 45 meters from the vertex. So that point would be at 0, 45. So we are given our focus. So I'm going to write down what I'm given. I'm given my focus. If it's 45 meters above the vertex, that means it's at the point 0, 45. In other words, I know the letter, do you know what it is? P. That's it. I know that P is 45 meters. That's the distance from my vertex to my focus. So now using sentence 2, I have P. That's pretty huge. What else do I know before I even get to sentence 3? Well, if I opened it going up, I could write the equation of this parabola, couldn't I? Or at least get it started. What would its equation be? Well, the equation of a parabola opening up would have which letter squared? X. Good job. So typically that would be x minus h squared. And if it's up, it's positive 4p times y minus k. But since we made our life easy by letting our vertex be at 0, 0, x minus 0 is just x, so x squared. P we know now, it's 45. And 4 times 45, that's really 2 copies of 90, or 180, times y. So now we have our model. X squared is really equal to 180y. So if we know the y location, we have the x location, and vice versa. Very helpful information. With our model now, so that was the goal, to create a model that described the situation. Now that we have a model, we can answer anything they have to throw at us. So let's take a look at our third and final sentence. It said, could you find the depth of this dish? And round your answer to 1 decimal place. So how would I even begin? Well, what does it mean by depth? If you take a look at your dish, we know that the width that it's opening is 100 meters. So where do you think the depth would be? How deep is the dish? Well, wouldn't it be this direction, the vertical component, at the opening? In other words, if you think of a vertical component, is that an x-coordinate or a y-coordinate? It's a y-coordinate, and it's the y-coordinate at the opening, wouldn't it be? Which would be the y-coordinate when x is 50, or the y-coordinate when x is negative 50. At that opening, that is the depth. So we have to do a little bit of thinking. I know we don't like that, but we have to think. So the depth is what we're looking for here, the y value at the opening. So if we're looking for, so here's what we want. We want to find the y when our x value equals what? At the opening, it's going to be positive or negative 50, according to the orientation that we've drawn. So how can we do this? Well, this is basic algebra now. Can we replace x in our model, in our equation? Can we replace our x with positive or negative 50 and solve for y? I hope so. If you do that, you would get positive or negative 50 getting squared equals 180y. Well, positive or negative getting squared is irrelevant. They're both positive, and 50 times 50 is just 2,500. So if you get 2,500 equals 180y, now you have the easiest type of equation ever, a linear equation. You can solve by dividing both sides by 180, and you should get your final answer. And now let's see if it makes sense. We should end up getting an answer of 125 over 9 if you use the fraction reduced form, or in the calculator, if you do the approximation, it's going to be roughly 13.9 meters when you round to 1 decimal place, okay, because the 8 repeats. Let's see if that makes any sense. Looking back at our situation, we knew that at the opening, it was 100 meters wide across, right? And now we're saying that if we went up about 14 meters, that's the depth. when we go out to our opening there. Notice also that the focus is beyond it. We're singling out our radio signals are focusing on a single point, which is 45 meters from the opening, from the initial vertex, right? But the actual opening itself is just going to be about 14 meters from the vertex. Okay, so that actually does make sense in our model. If our number was drastically bigger than 45, I would be a little concerned that our opening didn't quite make sense, because you should be focusing outside of your dish. Okay, well that's it for our examples today. You have a lot of practice because math is not a spectator sport, and next time when I see you, we'll be talking about our third conic section, the ellipse. See you next time.